morning. It's my honor and pleasure to be present in this inaugural function, along with our beloved Director Professor Gian, Professor S. Srinivasa Rao, Dean International Relations and Alumni Affairs, and Professor Sonione Sirish Hari, Dean R&C. Due to lectures, he is not present here, and Professor Muthu, who is in charge of today of Maths Department, along with our chief guest of today's function, and the total course is done by Professor Sergei Strachenko, Chief Scientist, Head Main Magnetic Field of Earth Lab, Russian Science of Academy, Russia. Here today for this Gian course. The present course is a continuation of a previous 10 days Gian course on magneto-hydrodynamics in the light of astrophysical dynamos, analytic, asymptotic and numerical applications conducted in the year 2022 during September 19 to 29. So in continuation with this is a second course. Even I can see some of the participants who attended that online course due to COVID, they are present here as participants. So I welcome them again. The topics of the present course are related to astrophysical and geophysical problems and also very attractive to applied mathematicians. Nowadays, the planetary hydrodynamics are subjected to a wide range of scientific and technology applications where the greatest achievements in analytic, asymptotic and numerical approaches are reached recently. These impressive approaches will be presented in the proposed course in the coming 10 days in the way that they could be effectively used in many other scientific and industrial applications. The proposed course is devoted to the hydrodynamics and critical convection of, especially to the rotating spherical layer planar convection, which models the liquid core of Earth and similar areas in the interior of planets as well as fast rotating stars. Emphasis will be placed in the mass, momentum, critical transfer of fast and slightly differential rotation in the liquid core of terrestrial planets, including moons and exoplanets. The course will cover various analytic, asymptotic, numeric solutions, explaining in detail about their methodology and practical usefulness for participants related to computational sciences, basic sciences, civil engineering, chemical engineering, physics, applied maths, marine, ship crafting, aircrafting, and many others. The course participants will learn these topics through lectures, hands-on numerical elements. Sometimes we are going to the lab for the MATLAB codes that will do in the practical and theory sessions. Okay, the objectives of this course is the main fundamental studies of planetary hydrodynamics, computational methods, and their interpretations for the basic hydrodynamic equations. So we have 35 lectures and 10 tutorials. These are the tentative schedule for this course. Already this course lectures have been distributed to the participants. So we have the participants from Arunachal Pradesh, Indore, Chennai, Vellore, Hyderabad, even from Khammam also, and nearby Warangal also. So I welcome all of these participants once again. Thanks to the director, deans, HODs, my colleagues, registrar, my scholars, my students in kickstart of this program very actively. I hope all of you will enjoy this 10 days. Thank you.
Thank you, ma'am. Now I would like to invite Professor P. Muthu, Head Department of Mathematics, to address the gathering.
Good morning to all of you. On behalf of the Department of Mathematics, I welcome our fellow director, Professor Gian and Professor Sergei and resource person for the 10 days Gian course on hydrodynamics and critical convection in liquid cores of terrestrial planets. Professor C. Rao, Dean IIA, Professor H.P. Rani, the coordinator of the Gian course, to the inaugural program of the Gian course. I also welcome Professor Maria and my dear colleagues from the Department of Mathematics and other departments and all students and the participants of the program for this function. I also welcome all the ladies and gentlemen to this inaugural ceremony. I will present the a brief profile of the Department of Mathematics here. Department of Mathematics is established in 1959 since the start of the REC Warangal. Earlier it was known as Department of Mathematics and Humanities. Since 2009 onwards, it is known as Department of Mathematics with an independent building. Presently we have 20 faculty members of regular position, 5 visiting assistant professors and 50 plus scholars. The department has 8 professors, 5 associate professors and 7 assistant professors. The faculty members are working in various branches of research areas, broadly grouped into 4 research areas. Number 1, fluid dynamics and mathematical modeling. Number 2, numerical analysis and differential equation. Number 3, operational research and statistics. Number 4, algebra, coding theory and cryptography. Department is offering the following 7 programs. Number 1, PhD in mathematics. Of course, we have various scholars with various fellowships, CSAR, INSPIRE, GATE, and many things, including self-financed also. We have second program called as 2 years MSc program in applied mathematics, which is started in the year 1970. And another program, 2 years MSc in Maths and Scientific Computing, which started in the year 2001. These 2 programs are most wanted program across the nation, and the admission is through the JAM exam. Similarly, we have another 2 programs, 5 years integrated MSc Maths. It started in the year 2021, and 4 years BTech Maths and Computing. These admissions are based on the JEE Mains. Similarly, we have 4 years BSc B.Ed Maths, B.Ed Physical Sciences, which is started in the year 2023. So we are also having another program called Minor in Computational and Applied Mathematics, which is as part of the National Education Policy 2020 guidelines. Also, the department is offering service courses to all the BTech courses and some of the MTech programs as a core or and elective courses at various levels. Almost 175 plus scholars are awarded PhD degree so far, and 30 plus projects have been completed. Faculty has published almost 800 plus research papers in the international reputable journals. In fact, our faculty members are serving experts in various levels of committees across the nation. Of course, I just mentioned the only 1 or 2 like R&D and many things here for sake of time. In the year 2023, we have conducted an international conference, ISTAM, in collaboration with the civil and mechanical departments. In total, around 25 or 30 conferences are conducted so far, and 80 plus reference courses like SCDP workshops are conducted. And now, this may be probably the 10th or 11th Gian courses in this department. The department has state-of-the-art computational facilities for our UG PG students and scholars, PhD students also. Once REC Warangal becomes NAD Warangal in the year around 2002, the department has expanded steadily along with the institute. Now our department is one of the India's leading academic and research center. I request, because one of time I am unable to present all the details here, so I request all the participants and others to visit our institute website for more details. In particular, you please visit the Maths Department website and see the faculty members' achievements, other research related information. Thanks to one and all. I wish all the participants to have a good time in the coming days and do the course very nicely. Thanks to one and all. Thank you, sir.
Thank you, sir. Now I would like to invite Dean, International Relations and Alumni Affairs, Professor S. Srinivasa Rao, to come forward to address the audience.
Good morning to all. Respected Director Professor Vidyadhar Subodhi, Foreign Expert Professor Sergey, Chief Scientist and Head Main Magnetic Field of the Earth Lab, Russian Academy of Sciences, Russia, Head of the Department, Professor P. Muthu, acting as an in charge today, and course coordinator, Professor H.P. Rani, research scholars, participants, and faculty members of the various departments of NIT Warangal. Warm welcome to all of you for this 10-day Gian course on hydrodynamics and critical convection in liquid courses of terrestrial planets. So myself, I am S. Srinivasa Rao, working as a professor in Department of Electrical Engineering, and now I am holding a Dean International Relations and Alumni Affairs from July 2024. So our Dean IRA office is looking after the international relations as well as alumni affairs. So you all know that the institute started in 1959 and the first batch completed their Diamond Jubilee celebrations in 2024. So at that time, BTech program is in 5 years. They passed out in 1964 and recently they celebrated Diamond Jubilee celebrations. Around 42,000 alumni are well connected to the institute maintained alumni software, and we are tapping the alumni who are occupying eminent fields for the benefit of the students as well as for development of the institute, and along with the liberal funds provided by Government of India. So along with this related to international relations, so we are looking after the Government of India sponsored programs like Gian, Spark, DAD, Heritage, MITAX, and many other programs. And along with that, the director NIT Varangal, Professor Vidyadhar Subodhi, is encouraging us a lot to make collaboration with foreign institutions and R&D centers as well as universities for making the international collaboration for exchange of faculty exchange programs and student exchange programs and international internships to the students of NIT Varangal. So we are rigorously working under the dynamic leadership of our director. So we hope we will work hard to make the institute international level of reputation. So along with that, related to this Gian course, in particular, Government of India initiated this program in 2015. We all know that the foreign professors will be called to Indian universities for delivering lectures, so that knowledge will be shared to the faculty as well as the research scholars of a particular institute related to the course content. So we have successfully participated in the Gian phase 1, phase 2, phase 3, and now phase 4 program is running on. In this phase 4 we have we got around 24 courses. There is a maximum limit of 50 courses to be submitted from each institute. So 24 courses were sanctioned in this Gian phase 4. So our success rate is very close to 50%. We are thankful to the Gian faculty members who are interacting with the foreign professors for making proposal for these Gian courses and submitting in time, and rigorous review process it went on, and finally the 24 courses were sanctioned and still some courses are under review. So the main objectives of this Gian program initiated in 2015 is to increase the footfalls of reputed international faculty in the Indian academic institutes, provide opportunity to Indian faculty to learn and share knowledge and teaching skills in cutting edge technologies, to provide opportunity for the Indian students to seek knowledge and experience from reputed international faculty, to create avenue for possible collaborative research with international faculty, to increase participation and presence of international students in the academic institutes of India, opportunity for the students of different institutes and universities to interact and learn subjects in the most advanced areas of collaborative learning process, provide opportunity for the technical persons from Indian industry to improve understandings and update their knowledge in the relevant areas, motivate the best international experts in the world to work on problems related to India, develop high quality course materials in advanced areas in form of video recording and live webcast, so that it can be used by a large body of students and faculty in India and also across the world, to develop and document a new pedagogical methods emerging topics of national and international interest. So from in 2015 in Gian phase 1 around 27 courses were sanctioned with a budget of 1.87 crores. In 2017-18 41 courses were sanctioned in Gian phase 2 with a budget of 2.48 crores. In 2019-23 21 courses were sanctioned under Gian phase 3 with a budget of 1.41 crores. In 2020-24 till now 24 courses were sanctioned with a budget of 1.75 crores, and few courses are under review. In this Gian phase 4, electrical engineering department got 7 courses, electronics and communication engineering 6, mechanical engineering department 4, Civil Engineering Department 4, Computer Science and Engineering 1, Mathematics 1, Physics Department 1. This was the mathematics course, only the one course sanctioned for the mathematics department in phase 4, that too for 10 days, 2 weeks program. So we appreciate the department as well as coordinator for initiating this process of submitting the proposal and getting accepted, and now we are able to meet outcome of that one. Until now, around 16 courses were successfully completed under GAN phase 4. Another 8 courses are yet to be completed. In all 4 phases, total courses sanctioned to NIT Warangal is Civil Department 27, Mechanical Department 16, Chemical Engineering Department 14, Electrical Engineering 13, Electronics and Communication Engineering 12, Mathematics 7, Computer Science Engineering 7, Chemistry 3, MME 2, and Physics 3. The total around 48 countries faculty are involved in this GAN courses from the countries like UK, USA, Australia, Belgium, Israel, Canada, Singapore, Germany, Italy, Japan, Malaysia, Europe, Norway, Portugal, Romania, Russia, Slovakia, Sweden, Taiwan, Greece, Denmark, France, England, Scotland, Finland, Trinidad and Tobago, and Middle East. In the recent past, so many faculty visited NIT Warangal under GAN as well as Spark programs, and also with some other invited programs by the faculty of NIT Warangal. In the past 4-5 months, many faculty visited and delivered lectures in Spark as well as GAN programs, and this institute got a lot of international presence for the past 3-4 months. Many people have come and delivered lectures, and a lot of knowledge sharing has happened. So we are very much thankful to Government of India for initiating such a nice program. This GAN phase 4 is monitored by IIT Hyderabad. National coordinator is located at IIT Hyderabad. We are very much thankful to Director IIT Hyderabad and Professor Anil Agarwal, coordinator, who is monitoring this all GAN phase 4 courses closely and initiating the process of reviewing as well as monitoring the course starting. And one day before the course starting, web links has to be provided and attendance of the participants list has to be provided. Such closely they are monitoring, and this course also it is recorded as well as webcast is essential. It is mandatory for this GAN phase 4 courses. Participants whoever has physically attended can directly interact with the foreign professor, and any other faculty or students or research scholars who are not able to register and getting selected for this course also can watch this course live program through web link, which is already there in NIT Warangal website as well as IIT Hyderabad website, and you can also approach a coordinator for getting that link. It can be shared to your friends, the research scholars and other faculty members, so that everybody will watch and maximum benefit out of this course has to be derived. It is all of our responsibility who are sitting here to share the web link to the whole world. That is mandatory of this GAN phase 4 courses. Under GAN phase 4, these are the faculty members who have visited NIT Warangal. Professor Shrikant Joshi from University of West Sweden, Professor Chanapat Paniswas, Queen Mary University, London, Professor Indrajit Chaubey, University of Connecticut, USA, Professor Tarun Athanraj, University of Edinburgh, UK, Professor Gian, National Nanyang Technological University, Singapore, Professor Rahul Jain, National University of Singapore, Ranjit K. Soman, Delft University, Netherlands, Lyon, Professor Lyon, University of Twente, Netherlands, Professor Israel Cohen, Technion University, Israel, Professor Rukmi Datta, University of New South Wales, Sydney, and many other faculty members have visited and shared their knowledge. Along with these people, so many foreign professors came under Spark as well as GAN course. The institute got an international presence as well as significance under the dynamic leadership of our director, Professor Vidyadhar Subodhi. So we all will work to make the institute reputation not only in India, throughout the world. So I thank all the participants for showing interest to see the title of the course and foreign expert and registering and getting selected for this program. So 10 days is not a small duration. It is like one full course. Along with the regular teaching duration, you can also interact with the professor. He is available in the campus for 24 hours. According to his convenience, you can interact and share knowledge so that our research we can enhance our research capabilities and also do the better PG as well as postgraduate programs, PG as well as research works. I thank once again Professor for showing interest and coordinating with Madam for initiating this program and coming all over from Russia. I am very much thankful on behalf of the Institute, sir. So your presence definitely makes a lot of significance for NIT Warangal. I wish you all the best to all the participants. Thank you one and all.
Thank you, sir. As we gather here today for the special occasion, it is now time to introduce our esteemed chief guest. To do the honors, I would like to invite Professor H.P. Rani, Course Coordinator, Department of Mathematics, to come forward and present the introduction of our chief guest.
Yeah, I'm so happy to read his short bio. I should say it is a short bio only because it went so many pages of his achievements itself. So now actually professor came from around minus 40 degrees, minus 40, minus 20. Now he said minus 15 there in St. Petersburg. From there to Moscow he flied, and then from there to Delhi, Delhi to Hyderabad. That is his journey. So there is a sudden switch of temperature from minus 15 to plus 20 here around. So thank you, Professor, for taking strain in coming over here. As a school by itself, he achieved many awards in Olympiads, in the all Soviet Union physics especially. He received a scholarship from Kazakhstan as the most outstanding student scientist in 1985. And in 1988, he defended his doctorate degree in Russia. Then after 10 years around, he became the Doctor of Science, the second degree, even at the age of 39 itself. From 2004 to present, he has been the chief researcher in Zimran, the prestigious Institute of Geophysics and Astrophysics. In 2007, he received the title of professor at RASTU. Sir, I don't know the full form of RASTU. Please explain that one. He is a recognized world community founder of methodologies that make it possible to find the asymptotic and even analytical solutions to the problem of convection, hydromagnetism, and the hydromagnetic dynamo of Earth, planets, the Sun, and the galaxies. So this is the topic of this 10 days program. He is going to elaborate about these things. He successfully predicted the magnetic field of Neptune, made the pioneering estimates of hydromagnetism of the planets, the wave nature of solar cycle, the statistical properties of geomagnetism, and also the importantly solar activity. Straczynsko's approach are already becoming classics in most of the hydromagnetic theories. He has led 23 Russian and also international projects, which together had a budget of about $1 million. He has chaired nearly 135 conferences and published around 300 scientific papers and 8 books, and has taken as a continuous active part in many scientific communities, councils, editorial boards, and committees. Sir is present before also in ISTAM 2017 conference, which held at Usmania University, Hyderabad physically, and in 2023, because of the COVID, as I said before, he did the first Gian course. I should say here, along with a student, Professor Maria here from Russia, Professor Straczynsko is present here to engage these classes. Yeah, Professor Maria came here for the Spark project along with Professor Sergey. So both of them are involved for the upcoming project, which is a specialized one, Spark project for the astrophysics and geophysics, including the mathematical relations.
Yeah, thank you, sir, for being here. Yeah, now I welcome to address the gathering.
Hello, I'm very honored to stay here in front of such a esteemed director, deans, professors, and some teachers, and especially I'm very glad to stand up here in front of so excellent students. I'm sure that the students are the main ingredient in this educational kitchen, if you like, because everything is doing only for them, because every student and who appears here is the future of the country. So we are trying to invest our time, the best knowledge and everything to raise the students in the field that they become more profound and can create the more scientific stuff and can be produce more science and mathematics and so on. So perhaps I also will add some small contribution to this field as far as I can be able to do. And in this respect, I am especially grateful to Professor Rani, Professor Rameshwar, who actually made all these things possible to have such a great connection with such a great people. Again, I stress that students are the most important. But nevertheless, of course, if it will be no such a wonderful person, such an esteemed person like your director, deans, professors, because namely they are creating this educational success, which eventually I am sure leads that India becomes one of the greatest scientific countries, because now you spend not in some material things, but things which is much over than material ones. So you are creating the true science which will help your country to rise up and maybe overcome all the other countries. At least in one respect, your country is now the greatest country, greatest democracy in the world, and in terms of population it's also big, and the way your government and of course through this government you are managed with the students and with all educational process is a very good way, and I think that the other country could follow your way, and in some sense you also try to involve different foreigners, estimated foreigners who has some success in different branches of the science, to collect them, and they are working on your success. It's very good, and so benefit, both sides are benefit. Of course, I am very great benefit because I am here and I have ability to extend my work, and you hope benefit from us, and everything could be wonderful, and I am sure that we are on the way, on the progress, and actually will do whatever is possible for the rising and for the glory of your country. Thank you.
Thank you, sir. It is now my honor to invite Professor Vidyadhar Subudhi, Director of NITW, to come forward and address us with their valuable sights on this occasion.
Good morning to everyone here. I'm glad to welcome the foreign expert today, Professor Sergey and Professor Maria here in this hall from Russian Academy of Sciences, Russia. And I'm glad that the coordinator Professor Rani could bridge the gap in the planning of this Gian program here for the benefit of the students, faculty and the participants in this very interesting area, hydrodynamics and critical convection in liquid cores of terrestrial planets. And the Dean has already mentioned about our activities. I am glad that NIT Warangal is a key contributor for this international collaboration and picking up the best minds, best experts from the foreign countries to Warangal and disseminating their expertise among the young, brilliant minds here. And I'm also glad the professors of the department like Professor Srinivasacharya, Professor Banerjee, Professor Datta, Professor Kashi Vishwanath and all of the faculty members are here to encourage this organization of the program, which symbolizes a good kind of cooperation and activity to nurture in the department to witness the success of the program. And to me it appears that this hydrodynamics has an excellent kind of contribution in today's mathematics, physics, electrical engineering, whatnot you just speak of. Because when you talk about the hydrodynamics, it is basically the conductivity of the fluid, and then the fluid dynamics basically related to fluid dynamics. And I believe that I'm just thinking that we are moving towards the electric vehicles or some kind of automotive sector transformation in curtailing the carbon footprint. So when you go for that, probably if I can visualize that if magnetohydrodynamics can be exploited to have no moving parts in the electric vehicles, maybe magnetodynamic based motors. So in that case, the moving parts can be avoided, and as a matter of fact, the kind of pollution and kind of energy wastage could be minimized. Maybe one upcoming research area one can think of. And this hydrodynamics has a lot of role to play, because the issue is that the friction, the rotating parts they produce, and the energy loss because of that. So therefore this is very, very, I feel it is a very kind of golden opportunity for the physicists, for the chemical engineers, for the mathematicians and for the electrical engineers to think about it, whether it is possible to channelize the thought to adopt this in the upcoming electric vehicle adoption in the nation. And so far as this hall is concerned, I believe the Department of Mathematics, in particular the coordinator Professor Rani, rightly picked up Chandrasekhar Hall. The name Chandrasekhar Ramanujam, when you talk about, they are the great scientist of the country. Therefore, the mathematician choose the Chandrasekhar Hall rather than Bose Hall or LC for organizing the same. And I also welcome the participants to this wonderful program. And how many PhD students are this hall? Can you raise your hands, please? How many MTech or MSc students are here? Very nice. Actually, the basic purpose of this GAN program is to invite the foreign experts who have very, very bright academic pursuit to share their knowledge and expertise to the Indian universities. So therefore, our Senate has made a conscious decision that not only the participants will be gaining the benefits, but also our own students, our PhD students and MSc or MTech students, or any student of this institute has a privilege of registering for a fractal course of 1 credit. So typically a 3-credit course, we engage the student for 42 hours to 44 hours. So in 1/3 of it. So maybe 14 hours, I think it's not uncommon in in this kind of teaching learning process. And I believe that the PhD students and the MSc or MTech students might have received a mail from the Dean Academy to register for this program. So then you will earn 1 credit if you choose to write an exam along with the participants. And if you want to simply listen without writing exam, yes, that option is open. This is in the audit mode. So the idea is that the Institute of Higher Learning like NIT Warangal would create an avenue for the students to learn from anyone who speaks in a new direction or a area which is relevant to your research or field of interest. So therefore, I believe that you, the student here, please propagate a message that in future, if the institute organizes a Gian or Spark program, consider it as an opportunity to register for the program, to earn a credit which you can obviously encash the same for your academic program you pursue over here. So with this, I again thank Professor Rani and the Department of Mathematics for conceptualizing this wonderful idea and to submit a nice proposal and get it a success, and inviting 2 of the foreign delegates, foreign experts here, and to invite such a large pool of participants and the PhD students and MSc and Tech students from multiple departments to be associated with the GAN program, and truly making the GAN program mandates or the objective of the country meaningful. I wish your learning through this program will be more fruitful to your academic accomplishments, and while the delegates from outside will take it a benefit not only to sit in this GAN program, but also to witness some of the places of their interest in and around Warangal. I once again thank the head of the department, Professor Muthu, and his friend or colleague, Professor Selvaraj, to support this organization of this program, and wish this program a great success. Thank you very much.
Thank you, sir. Ladies and gentlemen, it's now time to express our heartfelt gratitude to our esteemed chief guest for this gracious presence today. As a small token of appreciation, now I would like to invite Professor Vidyadhar Subudhi to felicitate our chief guest, Professor Sergey Vistarchenko, with a shawl and memento. As we come to the close of today's event, we would like to extend our heartfelt gratitude to all those who have contributed to make this occasion a success. It is now my honor to invite Professor Deepika Neela to deliver the vote of thanks.
A very good morning to all. It's my great privilege to propose vote of thanks on this auspicious occasion of the inaugural function of a 10-day Gian course on hydrodynamics and critical convection on liquid cores of terrestrial planets, organized by the Department of Mathematics, NIT Warangal. First and foremost, I extend my heartfelt gratitude to Professor Vidyadhar Subudhi, Director, NIT Warangal, for gracing this occasion, for his presence with support, and a special and profound thank to esteemed chief guest Professor Sergey Starchenko, Chief Scientist and Head, Main Magnetic Field of Earth Lab, Russian Academy of Sciences, Russia, for his invaluable time. A sincere thanks to National Coordinator of Gian courses, IIT Hyderabad, to make this program possible. I sincerely thank Professor S. Srinivasa Rao, Dean, International Relations and Alumni Affairs, and Institute Coordinator for Gian and Spark programs for his continuous guidance and support. And my deep appreciation goes to Professor Shirish Hari, Dean Research and Development, for his encouragement and constant support in facilitating this program. A heartfelt thanks to Professor P. Muthu, in charge head of the Department of Mathematics, for his support in organizing this course. I also extend my gratitude to Professor Abdul Azim, Chief Warden, and Professor J. Pranita, Deputy Chief Warden, NIT Hostels, for providing accommodation to the participants, and a profound thanks to Professor Shankar, in charge of Kalam Guest House, for providing local hospitality to the chief guest. A special thanks to Professor H.P. Rani, coordinator of this program, for her dedicated efforts in ensuring smooth execution of this event. I also extend my sincere thanks to all the faculty of the departments, deans, and head of the various departments, faculty members, research scholars, and MSc students, supporting staff, for their valuable contribution to make this event possible. Lastly, I would also like to express my sincere gratitude to all the participants for taking the initiative to attend this program, and that you will gain a meaningful insights and knowledge from the sessions ahead. Thank you all once again. Now I request everyone to rise for the national anthem.
शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे
for your demonstration of respect and patriotism. Now I request everyone to kindly join the group photo.
Battery is fine now. It's only 2%.
Tell them to change.
Thank you all for your participation and attention today. We are now delighted to invite you to join for a high tea, which will be served outside of this hall. We appreciate your presence and look forward to seeing you there. After high tea, a lecture by Professor Sergei V. Stachenko will begin at maybe 11:30 in this hall. Okay? 11:30, no? I gave 11:30.
मैम कितना कितनी करती आपको पता है ना स्नैक्स एक तो पीछे नहीं एक तो ही स्नैक्स क्या रखा ছিল wait okay go I'm not going to even have this snacks this one
Hello.
the literacy survey, which will be show how much is possible to do in the convectional style. Let's start from the goals of this course. This course of lectures is devoted to introduction to hydrodynamics and critical convection in a rotating and spherical layer, which models the fluid core of the Earth, like this one, of the Earth, and transfer in the simplest model of the fluid core of a terrestrial planet is considered. Course are designed approximately for 40 hours of lectures and practical classes during one semester. The original publication on the subject of this course, he gave corresponding lecture in Russian, the English, but it's necessary to mention that I gave the corresponding lecture in Russian almost 20 years ago, but the English version is sufficiently changed from the one which was Russian, because it was interesting to note at this point that very interesting progress happens since this Russian version, because when 20 years ago I made the Russian version, it has no this critical convection stuff, but it's considered only the consider. Oh, sorry. This mouse. Okay. Do you see mouse? Okay. So it was considering only differential rotation of the inner core and outer core, and only this complicated picture, but which is possible to consider in full, were considered in this previous Russian version. But eventually it appeared to be that things is not working like that. That basically it's working with vection. So about one half, maybe less than one half, maybe 30% or 40% come from the Russian version. And sorry? Pointer. Okay. But I may okay, you just keep it here. If you want. Okay. Yes, this is the point. Okay. But maybe I will show it by the mouse. Okay, in case. Thank you. So I just mean that this actually the Russian part of this course, which was demonstrated in physical department of Rybin State Aviation Technological Academy, now it's a university. For the period from 2000 to 2005, so it was different courses. So, but now the English version is very sufficiently transformated from the Russian version, because I think that even more than half about the convectional term, which was not available at all in Russian version. But of course the very basic things which consider the viscosity, equation of Navier-Stokes and so on, the same as in the English version, was very sadly changed, and its English version is now recommended by not only Russian Department of Geophysics of St. Petersburg University, but also from New York, Honorary Professor Rani, Professor Ramshaw, they also recommended for the presented here. So actually, it's to say that it's very different from the Russian version, and the main difference is in convection, which was no Russian. So you will first to go this convection to say general is this now, and after this of the it creates additional care in cook.
that the concept of infinity O square on the critical cylinder tangent to the inner sphere here. You see that with the of and you can see a mercury dynamo model geometries, different geometries. Geometry of A here shown. There is a thin shell model with the convection only outside the tangent cylinder. So there is a thin shell and convection only outside the tangent cylinder. Oh, where I lost the mouse. And where is mouse now? Oh, here. And then we can have B situation is here and B is here. And in B situation, there is a thin shell model with convective throughout the core. And the C model here, C model, a very thick shell model with isolated convectional clamps. And D model here, D model, sorry. And D model here, surrounding stable layer model, and E double dynamo model. So double dynamo, it's actually a double diffusion model. And meridian slice is shown in A and B, whereas the vertical lines is the rotational axis CE are equatorial slices. The solid in a core is shown in green, stably stratified layers are shown in blue, and convective instability layer are shown in pink. In A and B, long critical cylinder represents the convection rolls outside tangent cylinder. There are smaller critical presents more 3D convection patterns inside the tangent cylinder. And CE slices of the convection rolls are represented as ellipses. Okay, so this is work of Stanley and Glatzmar, but we should say that in some sense also it was my participation in the similar work which we done with Bassam and Soward, and it also could be applied to this mercury stuff in the case I don't know, maybe even in another case they considered many cases, but we considered even more cases for creating such a not so strong convection, which could consequently create a very strange magnetic field with. And then let's proceed to the next slide. And this difference of the thin and thick shells, which was just considered before, and different boundary condition can be clearly seen at this example here on the left of thermal convection in a rotating and spherical shell at Taylor number about 10 to 7, so 10 millions, 44 millions. Rayleigh number 10 to 6, so it's also very high Rayleigh number, and Prandtl number 1. This Prandtl number 1 is actually could be justified by the request that we consider turbulent convection, and here all the transport coefficient become the same, so it's quite useful maybe consider more simple, of course, becomes simple the Prandtl number. First column here show outer surface heat flux A. Outer surface flux, this is A case. Oh, I keep on losing the mouse. Sorry, where is that? Okay. It's A. And azimuthal velocity pattern is B. For the shell, which is aspect ratio 0.75 with stress boundaries. Second column is thin shell model. Here we have a thick shell on the upper row, and here we have a thin shell model. And the third column is a thick shell model with free at E and rigid boundary condition at F, and in CP left half is shown contours of zonal azimuthal velocity, right halves show contours of temperature in the equatorial plane. In contours from blue, minimum to red maximizing. Blue correspond to the minimum and red correspond to the maximum. Let's proceed to the next slide. I have many of them. Of course, it was possible to have even more, but maybe we are about the largest part passed. Hopefully we proceed further. And here there is, oh sorry. Oh, sorry. Okay. And so we have the preliminary modes and planetary-driven dynamo models with a thin unstable region lying above a thick stable region have been considered Stanley and Blocham in 2004-2006 as models for the Gian, Uranus and Neptune, as well as for the terrestrial planet Mercury. Here at this point it's necessary to mention that also this thin shell model for the ice giant Uranus and Neptune also was considered by us, and it was possible even to make the prediction, which I already was speaking a little bit, and this prediction was that the Voyager 2, when it fly by near the Uranus, it found quite unusual magnetic field, which inclined it not slightly related to the angular rotational rate vector, but very strongly. It was inclination about 60 degrees. And this 60 degrees allow quite unusual configuration of convection, which we suppose that it's due to the thin shell. And also numerical people much later found that this is possible. And our prediction for the next planets, next in terms of the visit of Voyager 2, is for the Neptune, and because a little bit another condition inside the Neptune, we predicted that the inclination of the dipole magnetic field is about 35 degrees. And as far as I remember, the Voyager passed it and successfully confirmed our prediction. We just roughly predicted 45, and they are measured 47 as far as I remember. So it's quite a good prediction. And also later, Bassam, Soward, and myself in 2011 also considered thin unstable regions, of course in the sense of the convection here. And but their focus was with the opposite case, where the unstable region lies below the stable region, and this leads to the interesting phenomena of penetrative convection. So convection penetrates from one region to another. And Takehira and Lister 2002 noted its relevance to the Earth's fluid core, where a thin stable region resides on top of the convective interior. This was Braginsky 1993. And it is possible that penetrative convection also occurs in the Jovian atmosphere, where the unstable and stable layers may be of similar thickness. Here the Jovian is shown actually. Previously, Zank and Schubert in 2000 identified a curious form of the convection that can be set up when the Prandtl number is small. And they found that also convection occurs in an unstable region. Additional quite vigorous convection took place near the outer boundary, well within the stable region. And also Zank and Schubert in 2000 coined the term teleconvection for this effect, so it would now have some value, this effect. And here you see the snapshot of the longitudinal winds maintained on the outer and inner boundary in a simulation of Jupiter using a Boussinesq deep rotational convection model. And reds represent prograde winds, blues retrograde. And it was worked by Stanley and Glansmeyer, which you use here just for illustration, this different situation. And next slide. We are almost over. And the simple Boussinesq model of thermal convection are highly idealized. For example, in planetary application, it is thought that both thermal and compositional convection occur, and it was by Fern and Loper in 1981. And investigation of the condition expected in the US core have been pursued Braginski and Roberts in 1995, and Bousset 2002 has found interesting result with two buoyancy ingredient on applying his unused model. So this is again maybe one of the first experimental double diffusional problem which was done Bousset in 1970. Indeed, the Boussinesq approximation itself is inadequate to capture some features, and the anelastic approximation is often better, as for example in application to the Gian planets, like in work of Stanley and Glansmeyer in 2010. And we remark in passing that Jones, Kuzanian and Mitchell in 2009 have undertaken the anelastic extension of the Boussinesq study by Jones et al. In 2000. And here you see the snapshot of the radial component of the convective velocity in the equatorial plane. It's left, and plane left, and the zonal winds in the meridional plane. It's on right. And for two anelastic simulations. The top row is for a case that is nearly Boussinesq, so spanning 0-point density scale height, and the bottom row is case with a significantly density stratification and spanning 5 density scale height. So it's a very wide span. On the right, green is upflow and blue is downflow. On the left, red is prograde and the blue is retrograde. And this is work of Jones and Kuzanian, 2009. And the next slide. And in the planetary type convection, one can see not only strong dependence on the geometry, but also on a set of parameters of convection. And here you can see flow in non-magnetic planetary type convection simulation at different parameter combination. And the top row is this one. The top row shows positive red and negative blue is the surfaces of the axial vorticity. The bottom row shows positive red and negative blue is the surface of the Z component of the flow, and the Prandtl number is unity in all cases. And this is the work of Wicht and Tilgner 2010, and the convective regime is also very dependent on Prandtl number for some value of the Boussinesq approximation, and actually it's not advised choice. And the last slide about this literature survey, 15. And here, nevertheless, much of the basic dynamic can be investigated within the simple thermal Boussinesq model, provided a non-uniform temperature gradient is imposed, which generally describes region of both stable and unstable stratification. See, for example, our work with Maria and Maslov, and in 2006. And there is also Simekan, Heide and Jankovic work in 2009. And in our work, with authorship of Tarchenko, Kotelnikova and Maslov 2006, authors adopted non-adiabatic entropy, which is directly proportional to the heat energy and has clear physical meaning. As a set of the thermodynamic parameters and considering almost adiabate approximation for the problem of global convection instability in a spherical shell. We have modeled the marginal stability of the compositional thermal turbulence geoconvection with Prandtl number unity as well equal 1. Extremely large critical Rayleigh numbers appears in this case when thermal convection opposes the compositional convection and some region of the core. Such opposition possibly occurs in some terrestrial planets in the late evolutionary stage. And the result for the onset of thermal planetary convection in the limit of small molecular Prandtl number shows that the value of the critical Rayleigh number sharply decreases with the growth of the inner core radius. This property can help to support the thermal convection even during the later stages of planetary evolution when the internal radioactive heat source becomes too weak or absent at all. Okay, so actually I made the small literature survey. Sorry if it was not so detailed, because it's impossible to go to the detail when you are observing so many papers. And now I hope to finish with the introductory part. And here I just very briefly consider the problem itself and what will be suggested to your attention in this course. So I think that the best picture for that will be this one. This one, which will give the general structure. So let me to read you out the preface, which will list what was done, which summarize what was done in this lecture course. And of course, we start from this very general things. So this course is developed to hydrodynamic phenomena that determine heat and mass transfer processes in the simplest model of the fluid core of the Earth and planets and moons with similar internal structure. So the structure here you see on this picture. And many natural phenomena that we observe can be interpreted as the transfer phenomena. For example, a weak electric current in flashlight and lightning are charge transfer. It's just a charge transfer, of course, no doubt. And an impulse is transferred by a pleasant breeze. For example, here we have pleasant breeze from the conditioner. Blowing around us and also could be destructive hurricane that sweeps away everything in the past. So there could be very different transfer, very severe, of course, as well. However, a hurricane can sometimes transfer even a massive object. Direct mass transfer occurs, for example, when a watch case is covered with a thin layer of gold during electrolysis. Heat transfer phenomena are extremely diverse. These include radial heating, convective heating transfer, radiation, and cooling. So there is a vast amount of different transfer. No, but it is impossible to study the entire diversity of transfer phenomena at once, and it hardly seems advisable. On the contrary, it is much more interesting and instructive to choose one such object on the example of which one can study both various isolated and combined transfer phenomena. As such an object, we will choose the fluid outer core of some planets. And first of all, of course, we will be interested in our native planet Earth. Of course, also it's to develop our curiosity, we will we will proceed further with other planets of the solar system, and possibly if we have enough data for the exoplanets as well. And the choice this choice actually was determined due to the professional interest of the author of the course. Another important reason that influenced this choice is the fact that it is in geophysics, namely in geophysics, that some of the most powerful methods for describing transfer phenomena have recently been developed. This method can be extended to many other areas of science and practice. From a formal point of view, the fluid core of the planet is a huge spherical layer, like shown in this picture. It is very important for all transport phenomena in this layer that this layer is rotating. So rotating is very much important here. For the sake of certainty, we will limit ourselves to studying the transfer of momentum, mass, and heat in this layer. It's already enough, and even not everything is resolved here. Accordingly, the first chapter of this course is developed to the most general ideas about the equations describing the transfer of mass and momentum in a rotating coordinate system. The concept of viscosity is directly related to the transfer of momentum and fluid, and formally the entire diversity of fluid flows are described by the system of hydrodynamic equation, with the main equation in the system being the Navier-Stokes equation. Of course, it's also derived. The first chapter ends with the detailed solution of two problems of varying difficulty. This gives teachers and students a clear idea of how to solve the following problems in this course. An example of a possible short solution for the last problem at the end of this third chapter is also given. And to apply a hydrodynamic system to a rotating spherical layer, it is necessary to write it in rotating coordinate system. To a rotation to apply a hydrodynamic system to a rotating spherical layer, it is necessary to write it in a rotating coordinate system and consider all the main similarity criteria for it, which is done in the second chapter. So now we proceed into the second chapter description. Among the many possible similarity and criteria, two of the most important of them are related to the fact that the rotation of the spherical layer under consideration is almost rigid and fast. Here the Ekman and Rossby number are extremely small. Ekman and Rossby number, as already I mentioned to you, for the case of the Earth, Ekman number is 10 to minus 15, and Rossby number actually 10 to minus 9 to minus 10. It's not okay, but it's also very small. Therefore, in the main volume of the spherical layer under consideration, the corresponding internal and viscous forces can be neglected with a high accuracy. So it's quite important, which I can give rid of the many terms, and it's highly simplifies the equation and way to solve it. As a result, relatively simple equations are obtained that describe a geostrophic flow, which in the absence of the buoyancy force is reduced to a differential rotation of the liquid, which depends only on the distance to the rotational axis. The specific form of this dependence is determined by the viscous forces that act in extremely narrow boundary and shear layers. Let's proceed to the third chapter description. This chapter is devoted to the viscous flow in narrow Ekman layer, perhaps one of the most important layers. which are directly adjacent to the rigid spherical boundary of the layer under consideration. In essence, it is this active hydrodynamic layer that largely determines all the main characteristics of the flow under consideration. What is remarkable is that it is possible to completely analytically and relatively simply describe the flow in this linear Ekman layer. So it's also a very important point that Ekman layer and the description of this is completely linear, even for non-linear problem, because actually this term which appears from the non-linearity, so this term V grad V, this Rossby term, is because the Rossby number, namely Rossby number, is very small. So this term we can actually neglect. And so the problem in effectively way for the Ekman layer becomes linear, and we can precisely solve it. And so this idea is very interesting to use in numerical calculation, but I didn't know anybody who tried to apply this idea to avoid the singularity near the boundary, just to apply this. So maybe this is just idea. Hopefully somebody develop. Let's consider the chapter 4. Chapter 4 derives and discuss general equation for planetary convection driven by heat and mass transfer due to convective instability caused by thermal effects and gravitational differentiation of mass. In the Earth's interior, differential dominates, as a result of which the more massive component, mainly iron and nickel, of the liquid core settles on the solid core, as I already told you, and the excess light admixture, apparently based on sulfur, oxygen, etc., floats up directly, and this actually directly generate convection. Thus, such a differentiation is almost 100% efficient in a mechanical sense. More precisely to say, if we consider the thermal effect of this compositional convection, it's efficiently even more than 100%, because during this crystallization of the liquid, we have some additional heat flows which support additionally. And in fact, this conditional efficiency is even greater due to the change in the state of the matter. The substance from liquid becomes solid, and the release of the heat, consequent release of the heat, as I told. This heat locally released at the boundary of the liquid core, with the solid core, again directly supports convection. Much less efficient are global heat released due to the cooling of the core and radiation effects. Moreover, it's necessary to mention here that this thermal effect even could have negative influence on the generation of convection. It can even stop it somehow. It's possible because there are some measurements from the seismic research and so on that there is a stably stratified layer, and it's this stably stratified layer on the top of the liquid core, and it's due to the thermal convection, which not help to convect. Not thermal convection, thermal instability, because it's some condition which is very similar for the Earth. It could be not thermal instability, but the thermal stability. Moreover, within the framework of modern views, these global effects may even partly suppress convection, as I told. Such an effect is unlikely also possible in the Earth's core, but is most likely present to the fullest in the depths of the Mercury and Ganymede moons of Jupiter, which consequently generate a very small, observable and internistic magnetic field, and quite unusual is it. Despite such a somewhat flat role of thermal effect in terms of maintaining convection, this effect in fact determines the thermodynamic characteristic of the convectional process, since it occurs near the adiabatic equilibrium. And the last, but not the least, of course, maybe perhaps even the most important, is chapter 5, is the final one. And this chapter describes critical convection, which determines the excitation, the threshold, the temporal and partial structure of heat and mass transfer for the most basic state of practically linear planetary convection. It is remarkable that the complete solution of the very complex system of partial differential equations is reduced to solving a second order ordinary differential equation, as I already told you, and the parameter of which sets the input condition of the problem. Or maybe I here say the very important but the things which I truly believe. I dare to suggest that this is the most impressive and radically breakthrough in constructing simplified and at the same time very accurate solution of real physical system. The value of this breakthrough is further aggravated by the fact that we cannot conduct experiment with the planets. However, having the asymptotic methods described within chapter 5, we can widely vary the input parameter until the output parameter agree with the observation of the like planets and moons, both in solar system and outside it. And I, of course, invited all the people to join this brilliant way and to try to model not only in our system the planets, which is not completely done, but in other systems for exoplanets and exomoon, if you like. Okay, so seems I finished. I don't know how many times I spent. I didn't so. Okay, maybe I have finished with this introductory part. So, as far as I understand now, maybe there is some question. Maybe there is some question to the introduction part. Yeah. There are various numerical methods, but the expand the spherical harmonic. Spherical harmonic. They use the spherical harmonic, you know, that which appear close to the Gauss theorem. You have Gauss Laplacian and the extent in natural spherical coordinate, you are getting the spherical harmonic. So you use the spherical harmonic as a base, and it's actually a unique picture of almost all models that use the spherical harmonic. But the difference between models is that what they use in the radial direction. There are different approaches. Some approaches they have this radial mesh, which is more concentrated near the boundary because boundary is necessary to resolve. And near equilateral of the image of also they, and also there is direct, also in some polynomials, in some special functions, so there is no unique method for the radial direction. But almost all are in the, for example, for the azimuthal component and this latitudinal component, we have the spherical function. So actually this is, of course there are some works which is just extended in the direct numerical simulation, not by the means of the spherical component. Especially if you consider the plane layer, it's also very popular. Of course here we have different approach, but to my recollection, if we consider a sphere, usually we base on spherical function.
Double dynamo planet is then
Sorry?
double dynamo planet.
Double dynamo?
Double dynamo region.
It's actually the Earth dynamo is double dynamo, maybe to better сказать, not double dynamo, double diffusion. Or you mean that the dynamo different region?
Dynamo region different, two dynamo region.
Yes. Actually, this idea about two different dynamo regions is one of the first was suggested by Makarov, Ruzmaikin, and myself. It was almost 35 years ago. And we just suggested that the different waves of the solar activity, we know that there is a solar activity which is working 11 cycle. But there is another branch of the solar activity when it moves not the solar spots, but this feature which is possible to see in some sort of the polar magnetic field. They move to the pole. So there is two waves, two clear waves. And so we considered that the most impressive wave about the solar spots is created in the deep region of the convectional zone and just penetrate. And this is another branch which is close to the pole and has more weak magnetic field. So, for example, in solar spots we have 1,000 Gauss, and here we have just some Gauss, maybe 10 some maximum. And so it's another wave which is maybe somewhere in the middle of the convection. We even suggested third one, which is on the surface. So this is actually it's possible even 3 dynamo regions. And if you consider the namely 2 dynamo regions, there is also Christensen model of the Mercury. You also consider, and also we a little bit consider this situation just to describe the convection. But frankly speaking, this point is not so popular. These are the people who prefer to model all the everywhere as not separate them from different scale because they actually connect. Okay, thank you for the interesting question. Yeah, please.
Is there any relation between the speed of rotation and turbulence inside
Yeah, of course, there is a very interesting. If we consider this relation, it's interesting in the sense that when in the relative term, of course, in terms of Rossby number, for example, when the angular rotation is not so long, small but not that small. There is a background dependence. But then the rotation will become more or less strong, really number, Rossby number very small. There is almost no influence on the turbulence. It stabilizes somehow. There is even the law which from this law is created by the magnetic field and some turbulence. There is some sort of level of saturation. So if you have angular rotation that's strong enough, so we have stabilization in this direction. And everything is stabilized, and this actually further, if we further increase the angular rotation, there is no dependence at all. It's interesting. Well, thank you. One question, please.
This cylindrical is considered as a planet itself to this
The cylindrical coordinates considered, because here you see that if you consider, of course it's spherical coordinate system initially, but if we consider, for example, the case when the sphere are rotating slightly at different angular rotational rate, even very slightly, then we eventually have the layer on this, exactly on this tangent cylinder. Because why we have this Kangen cylinder? Because on the fast rotation, we have the the dependence tends to be not independent in the rotational rate. In the vector of angular rotational rate, there is almost the same picture of the convection if we move from the one point to another. While it will be quite with less characteristic size and concentrated if we move in this direction. So eventually it ends up with the case we should consider cylindrical section. The most interesting section is the question of
Thank you. Thank you. We now proceed now, and this is our first paragraph of the first chapter, consequently. So we are starting with the definition of viscosity. Let us begin with an important experimental fact. This is purely experimental. It turns out, also in the fun from obviously, also it is far from the obvious, that in all cases where this has been verified in practice, the velocity of a fluid on the surface of a solid body is exactly zero in the coordinate system associated with this body. It seems somehow obvious, but of course somebody don't understand why it's so. So you have noticed, of course, that the blades of a fan collect a thin layer of dust. It's quite interesting that the fan is rotated, but nevertheless there is a collection of the dust on it. And this despite in the fact that they are spinning rapidly, very rapidly in the air. The same effect can be observed even in a larger wind tunnels. In the larger wind tunnels. Why is this dust not blown away by the air? This is actually a problem because in all fastly moving objects, especially they cross some dust sphere position, there is such accumulation of the dust. The same effect can be observed in the large wind tunnel. And despite the fact that the blades of fan are, velocity are relative to them measured directly on their surface is zero, so that the air flow does not disturb even the smallest dust particle. Even the smallest dust particle, if they attracted, it's impossible because the flow exactly zero. Thus, in our theory, we must take into account the experimental fact that in all ordinary, or more formally in Newtonian, of course we should name our new fluids because there are different fluids. There are fluids, for example, fluid crystals, and they have another properties, but this is Newtonian for fluids. And the molecules located near the solid surface actually experimental fact, and also we see that. And ideal, so let's consider some ideal or dry fluid without viscosity is characterized by the fact that if any small shear stress is applied to it, it will inevitably give in to this stress and flow. A real of viscous fluids, on the contrary, resists shear stress. Viscosity, despite these forces that arise in a moving fluid. To estimate such shear forces that arise during the movement of a fluid, consider two parallel infinite solid plates with a liquid between them. This is a very simple picture with two fluids. So see there is on this picture you see that the solid plate with a liquid between them. So this is the cross section of this solid plate, and there is a distance on which there, and also directly to our face there is a plane is moving. And of course it is some approximation. And we suppose. In addition, one of the plates, so there is a two plate, but one of the plates, the lower one in figure 1, because here there is this lower plate, and this, in addition to that, it is stationary. So one plate which is below in this picture is stationary, while the other moves parallel to it at the lower speed to 0. So there is lower speed to 0, and the upper plate is moving with this speed. So actually, by measuring the force, there is a force F which is required for that. To maintain the motion of the upper plate,
we find that this force is directly proportional to the area of the plate. Of course, this place could have some restricted areas, or of course not necessarily infinite, but and also the ratio. So actually, there is a problem of the area of the plate, and this sort of the gradient of the velocity. So this is actually 0 divided by t, where t is the distance between plates. And there is a distance between plates, and in this way the shear stress sigma and the coefficient of dynamic viscosity, or in short, simply the viscosity eta, are determined. So actually this is the first and even zero formula in this. Also, it's supposed to write it down. So it was to write it down, so it will be first formula of the force. We have F divided by S, and it's equal, by definition actually, if we have 3, so it's by definition. So it's equal sigma, so which is definition of the stress actually. And in fact, from the experimental fact, we should notice that it's equal the coefficient of the viscosity and 0. 0 is this special notation that it's relatively slow velocity, because of course if it's very big, then the law is not so easy to manage. And also distance between plates. So this is actually the first formula, and we mark as first digit is the number of the chapter, and the second digit is the number of the formula itself. And because this is a very basic formula, so we decide to make the index 0 to it, because it's quite important for the formula. So in this way, the shear stress sigma and the coefficient of dynamic viscosity, or the short simple viscosity, could be determined by that, as I showed in this problem. So it's quite simple definition. And also we can proceed further that in other words, and every point on the real fluid, when of course we should consider relatively small plates and relatively small distance between these plates. So we just can rearrange this formula to this another formula. This another formula which is shown here for the general purpose. And this is sort of the definitional alternative definition. And but it's maybe not so important, because so we shift it just for we are showing it just for some understanding how it's works. And also, so is it, and at every point in the real fluid, the shear stress at every point in the real fluid. So we can see the very small space and very small. All these quantities are very small and very on very small distance related difference. So actually we are getting sort of the derivative of the velocity in respect of the radius. So it could be also alternative definition of the stress and viscosity like that. So at every point in a real fluid, the shear stress, this is actually the shear stress, is directed along such parallel spaces of an infinitely small parallelepiped that are separated from each other by a distance delta r and move related to each other with the velocity delta u. In the general case, moving to the differential form, we obtain that the local shear stress at point in some infinitely small area. So of course we now proceed to infinitely small area because we want to formulate all this formula in this infinitely small areas and other derivatives, other things that we are using here. And this actually we can write the next formula, important formula of our course. So because there is a two-direction, and we can introduce the coordinate system for that. And finally, we have definition of the stress. We have a definition of the stress that is the stresses will be defined like that. And we put special indexes on it, distinguished from other, and then it's actually equal viscosity multiplied by derivatives, partial derivatives of x component of it, divided by dy, and plus by dx, also x. So this is the formula, next one, formula. One can easy to see that there is sort of the cross. If we are taking the derivative of one in one y plate, and so it is a cross. Here we have derivatives of velocity, and here we have derivative of velocity in x direction, and here on cross we have derivatives also in x direction, and here there is another cross. Here we have derivatives in y direction, and also we are taking y component of the velocity. So this is sort of the cross, too easy to understand how it works. And if the fluid is in solid body rotation, then the velocity derived in one above must be equal in magnitude and opposite in sign. In sign, since in solid body rotation it is natural to expect that the shear stress is zero everywhere. This is proved at the end of this chapter in the detailed problem 1 using figure 2, which illustrates an arbitrary rotation of some solid medium in a stationary Cartesian coordinate system. This is picture. So it is here that it's rotated at some angular velocity vector omega. Omega is arrow on it, it's with vector. And so it is a coordinate system, and there is a point which we are considering. So there is a velocity here, and also radial, and also there is also the component which we already listed, Cartesian coordinate x, y, and z. And then, in contrast to the idealized infinitely extended system, the cross-section of which is shown in figure 1. Figure 1 is the previous figure, which is this one, which is shows these two plates. Of course, very much a divided figure. So, and the real system but in contrast to the figure 1 in picture, the real system for determining viscosity consists of two slowly rotating coaxial cylinders which are separated by the measured fluid, C figure 3. So C figure 3. There is a C figure 3. So actually, to measure the viscosity, we will use such a picture. C figure real cylinders are not infinite, but their length in the direction proportional to the plate of figure 3 usually greatly exceed the radius of this cylinder A in B. So actually to measure the viscosity we use such a cylinder which rotated with different speed. So this inner cylinder and outer cylinder and then rotated with different speed. And also we consider some position which we consider, and so then here we have different velocity and which of course change somehow, and how it's changed is obvious some equation. Usually in this figure 3 we show, and this is actually experiment. In figure 3 we just see the experimental determination of viscosity, which is possible to do if we rotate two cylinder. Of course we cannot make this cylinder infinite, but if they will be long enough in comparison with their cross size, so that it will be a good approximation. And then let us denote the instantaneous angular velocity of rotation at distance r from the axis of rotation is just omega. Just omega, this is which in all these formulas is just omega is appeared. Accordingly, the linear velocity U will be equal to the omega r. So omega r is appears somewhere here as well. Omega r. And with sufficiently slow rotation, it follows from the experiment that the angular velocity will depend only on the distance r. So experiment shows that the angular velocity will depend only on distance r. So we can state that actually this angular velocity omega is some function of r, whereas the r is the cylindrical radius, some cylindrical radius. So we have that this relation omega is f from r, and the coordinate of the an arbitrary fluid particle will therefore change according to the harmonic law, because of course we got from r. So the harmonic law is quite well understood. Everybody knows him, that I don't comment. There is a cosine part which will be related to this with the Cartesian x coordinate, and also there is a sine part of this harmonic law which is related to the y coordinate in this picture. And so we can easily take derivatives and we get this velocity. Let us determine the velocity component that differentiates in these coordinates with respect to the time, and assuming that the flow has already set and omega does not depend on time. So we have some sort of stabilized situation, but everything is somehow set. So in here we have the next formula which is written here. So we can just take the derivatives, and it will be represented. Omega is coming out after this operation of derivation, and also minus coming out from the cosine when we take the derivatives. And otherwise we can write this with the same relation as the minus omega by y. And the same manipulation we can do with y component of the velocity. We also make the derivatives. Now it's positive relatively, and so we have the same relation, which is very similar, but also in simply it's just this plus sign and omega another. So again we see sort of the cross. Here we have x component and y consequently we have here in this relation. And here we have y and consequently x is here. So this is interesting feature. So we use formula 1, which I wrote here, this is formula 1. And so then we obtain that the shear stress is equal to the following relation. Okay, we do that, and then we make some transformation, and then we have just using the formula of one, this formula, we can find the different component of this stress term, and the intermediate result is possible to write down here. Okay, maybe it will be more interesting to use this intermediate result. You will do by yourself, and I will proceed to. There is some intermediate result which you can transform when we do this component, and so we transfer to the different points. So first intermediate result is shown here in this picture. So we have this stress which is in XY plate, and then we can consider that there is such a relation between all these corresponding derivatives and corresponding coordinates and corresponding to r, x, and y. And you see that this is the universal relation, but maybe not so important. You can manage with them by yourself. And eventually, in practical for points with coordinates y0, we have these relations. And accordingly, in the cross section of the plane layer, y equals 0, we obtain. Now it's important formula. Let's write it down as well. And by the way, it will be quite useful for you if you write down the formula, not only read them on the text, but tactical situation is very important. When you are writing down some formula, you much better remember it, and much better can then use the way. So it's quite useful. So let's write down the next important formula of this number. And this is, we mark it that we are determining this stress component at the point where y is equal to 0, more precisely at the number of points. And then eventually we have very simple relation that viscosity multiplied by r, and differentiation of omega. Omega, of course, change with r, and this is the r. So this is sort of the general relation, and we can number this formula as 1.2. Now, from the symmetry of the problem, it is obvious that the tangential stress 2, which just we write down, is the same for a fixed radius of r. Let us now find the moment of force tau acting on a cylindrical surface of radius r. To do this, we multiply the shear stress 2 by the level on vector r and by the corresponding area of the cylinder to PRL. So this is the current flow area of the cylinder, which consists from the PRL. I just write this down. It's the PRL. So this is the area of the cylinder, so which we use, it's an intermediate formula. And so finally we have that this tau is equal. So I remind you that the tau is the moment of force acting on a cylindrical surface at radial step. And this tau eventually become actually, this is the next important formula 1.3. Since the fluid flow under consideration is stationary, the total stress acting on the volume, see figure 3 is just previous figure. This one. Suppose that the time from the symmetry Vegas now. So since the fluid flow under consideration is stationary, the total stress acting on a volume must be equal to 0. That is the moment 3. Moment 3, I named it 3. This formula. That is the moment 3. Must not depend on the radius. So actually, otherwise we are not in our area. Otherwise, a shear stress accelerating or deaccelerating the rotation will arise due to the difference in stress at the boundaries of the cylindrical layer shown in figure 3, located between R and R plus the arc. So actually, we are considering the shell which are between R and R plus the R. Therefore, the moment 3 is equal to a constant which using other constant A and B, we denote them like okay. Two pinions are light, but you see this in the picture. And so 2p neutral. Okay. We choose some arbitrary constant which we define it later. And then we have this formula which is written here. And it's again very important formula. Maybe not so very important, but at least on this position. So we can write down here, there is some space for it. But because the omega depends only on R, we are using the direct derivative. The omega R is equal to A over R cubed consequences of that, we can show it by such error. We have that the omega, just making the simple integration, we have the omega is equal again some constant b minus a divided by 2s squared also. And this is formula 1/4. So that of course there is obviously that we can define these two constants via the sort of the boundary condition. In our case below this formula below, and so we just have this boundary condition. Boundary condition. And eventually we have the final formula when we collect everything back, and we arrive to the final formula. This final formula is, again, I think that it's here. So this S tau, which we are looking, moment of force tau, sorry, which we are looking here at the position of D, is equal to E atom would be better A squared. And then there is the ratio. First of all, we have more faster rotating radius B because it's no longer. Then we have a bit slowly rotating omega A. And here we have the difference between squares of radius of the outer boundary and the inner boundary. This is over 1 side. This moment of force is measured experimentally by dynamometer. So we can use the dynamometer which measures this force, which is attached to the outer cylinder. Outer cylinder is with radius d. In this case, the inner cylinder, as a rule, rotates uniformly, and the angular velocity of rotation of the outer cylinder is zero. So the easiest way just to rotate inner cylinder and just to stop somehow outer cylinder. In practice, the kinematic viscosity coefficient here you see, also kinematic viscosity coefficient is used more often. So because let's define the kinematic viscosity coefficient. So we define the kinematic viscosity coefficient actually by definition. And this is relation of the dynamic viscosity on the density. So this is important definition, so we could both what we say. And if we consider, for example, some liquid, of course the most close to us liquid is the water. So for the water it's about 10 to minus 5 meters squared per second. So this is the actually universal, so it has no any what is related to. So okay, we can it is interesting fact that the viscosity of the water is very close to the viscosity of the fuel under the condition in the earth floor. So it's also such small. There is, of course, variation. It's impossible to exactly to measure on such condition in the earth. This viscosity, so it's actually of this liquid metal in the earth, viscosity is usually from estimated from 10 to minus 4 to the 10 to minus 6. So, and it's also even possible to measure this viscosity in the real physical experiments. And another way, just we are making the model of the Earth, then test it on the earthquake. It's like we are using ultrasonic to define the danger of the baby. So here we use this earthquake, and from this earthquake we can actually extract the density and many other thermodynamic component, and then supposing some model of the matter which is basically fair, and we can estimate this viscosity as well, but maybe not so precisely. But nevertheless, it's important to know about. And such kinematic viscosity is obtained as a result of dividing the dynamic coefficient of viscosity at by the density of the liquid R, as I wrote here. And as noted in Formula 6, almost practically important fluid has the same order of magnitude. It's interesting that for us the most important fluids are water, but for the people who are living the hell, because we usually down support that the hell, and this hell they have the same viscosity, but they live this hell. Okay, that's just a joke. This kinematic coefficient of viscosity is also referred to as just kinematic viscosity. So just to make it shorter. And sometimes, and even more often, it's just named viscosity without any remark. And usually you see here viscosity is basically kinematic coefficient. But sometimes it's another. Okay, it seems we finished something about viscosity. Is it enough?
Yeah.
Okay, maybe there is some question about viscosity.
No questions? We go for your tea. Take your break and next one.
Is there any question about viscosity?
So the question 1, in the question F by S belongs to
Sorry?
in question 1.0 F by S.
I also
That's S is
Surface.
It's area, yeah, it's area.
Surface area. Just a little walk. We go to the Nescafe center and take tea.
Pressure, you know. What is pressure? T is equal to
I plan like that. Instead of sitting for hours together, tea can come here also. But we go a little bit there. Outside. Okay. Nearby we take the tea and we come.
So we have break.
I mean, Mochappino is there.
So how long we have break? Huh?
Half an hour.
Oh, half an hour. Ah, it's 4.
4 o'clock.
At 4 we start, yeah.
4 o'clock.
a small particle of a viscous fluid moving with velocity u is an equation describing in differential form the transfer of momentum by this particle. In its most general form, this transfer is determined by the following relations. Here I just want to stress that this equation perhaps is not perhaps exactly the central equation in hydrodynamics. Sometimes it's named Navier-Stokes equation, sometimes it's named momentum equation, just momentum of force. And so actually this is very important equation, so it was to write it down. And so let's write. Okay. Oh. It's not removed. Oh. Oh. Oh, okay. Some forces needed. Second law. Yeah. Professor has no force. He invented all his forces to the not material, to the ideal. Oh, maybe we use another stick. Maybe this is better. Okay, thank you. We're almost finished. So I just commented on this important law because actually it's again the second law in Newton's second law of the forces, perhaps maybe some most important. So here there is also important, and we are looking for the force balance. And this force balance is actually we can use different forces. Of course, first of all, we try to use the forces which has hydrodynamic nature. And so let's write it down. So there is a raw density on the first place. Then we have partial derivatives of velocity. Velocity vector, important that it's vector. These partial derivatives in t. Then we have the part of the full derivatives. If we consider the movement, then we have this vector u multiplied by gradient, and all is this acting again on vector u. So this is the transfer, but direct transfer, not like a viscosity. Okay, thanks. Okay, now it's going blue, because actually we are considering the liquid, and it's usually not dark, but it's blue. So now it's equal. So this is the force, which is actually acceleration force. In the Newton's second law, it's just all this term we can relate as ma. Oh, sorry. M multiplied it, mass multiplied by acceleration. So all this first term is working like that. So then we can add different forces. For example, of course, one force we already considered, so we put it on the first floor, first place. Okay, you know that force? Is it? Viscosity, exactly. And then there are another forces. At the moment we will not specify them, but they could be quite different. For example, if you are fond of the magnetic field. It will be the Lorentz force. If you are fond of the source of the convection, yeah, it will be the field of the acceleration, the bi-acceleration, which, yeah, and so on. There are a vast amount of them. In some complicated cases, if there are impurities, so we have very many of them, and of course it also could be another forces. But for us, the most important thing which we separate out of this force, this is sort of the general force, but there is one force which is still also important, and it should be mentioned directly, because this is related with the hydrodynamics and with thermodynamics, no, not hydrodynamics, with thermodynamics. And you know this force. What is that? Huh? Pressure. Yeah, pressure gradient. Gradient of pressure.
So if we operate more or less simple stuff, we still have from thermodynamic variation, we only have pressure. But if we go to the more realistic and complicated cases, we should add temperature and so on, variation of density and so on. So let me stress again about this very important formula. I even write it. There is a density multiplied by partial derivatives of u and by time, and also usually this term is named Rossby term, and it's actually the major sources of all turbulence and so on, and also it's source of the nonlinearity. So in the problems where the nonlinearity is important, it's playing some central role. But I revealed some small secret that actually in our field, which we are looking for, this term could be very small. So there is a great advantage which simplifies the problem a lot. And we can find even almost exact solution for some problems which I will show later. So again, I just remind that rho is the fluid density, F nu this is positive force, directly dependent on changes in the velocity of the fluid. F is external non-viscous
fluid particle, and P is standard.
I don't know when this equation was actually derived, but because it's named Navier-Stokes, so it's actually this person which was in the last century, always the last century, because as far as my recollection, in the beginning of the previous century, it already was Boussinesq solution. So maybe 200 years ago, something like that, it was invented, and it's still working perfectly. So I already told you, this is a unique term in somehow, which is related to the, if we make some analogy with Newton's law, so it's related like the product of mass and acceleration. And another name for this term, which flow together, is the total or substantial derivative of velocity. Enclosed in square brackets here, this is total derivative of the velocity. Describe the acceleration of an infinitely small fluid particle. So actually we can use standard rules for differentiation a complex function, and it's useful to present these derivatives in an initial Cartesian coordinate system. So we just can use the standard rules of differentiation and complex function, and we get this term which is here in square brackets. Okay, now you see how it's locked. So it's what we are actually doing. We are first how to take this, somebody call it substantial derivatives, somebody call it full derivatives. Yeah. So, okay, let's call it substantial. I don't know why I call that now, but because for the reason. So it's substantial. So now we have du vector u, which in fact is dependent on time, x coordinate, y coordinate, Cartesian coordinate, and z. And also it's full before derivatives in time. And now we proceed as a complex function. First we divide it by ordinary, getting the ordinary derivatives, just taking the first term, so it will be du by dt. Then we proceed further. We take derivatives of x, and this derivatives of x is also dependent on time somehow. And again, by definition, if we make these derivatives of x with t, we are receiving the x component of the field. So we have du vector, du vector by dx, partial derivatives. And now we derive x itself. It now will be straight derivatives. Just for the fun, I maybe write it. Just to have some small difference, let's do it in a little bit another notation. So we just, here we should have direct derivatives of x by dt, and often it's just denoted by the point on the x. So now we have x component. Then of course the next is coming, so we have du by dy and y with point. So now you understand that the point means derivatives by t, direct derivatives, not partial. Then the next one, du by dz, and again z with point. Okay. And now you see that you can just equal x is dx, y is du y plus, oh sorry, plus, why I wrote the plus. Oh, maybe we even do that such way. So it could be replaced by that. And this could be replaced. And so straightly not writing this Lance formula, we see that it's just by definition this term. Because here in Cartesian system we have all these components which appear in the proper position. So this is the formula 1.8 and this formula 1.7. So we have such a result. So if the viscous force F nu is equal naught,
if the viscous force is equal naught. Okay. No, not yet. Then equation 7 will be an equation for an ideal non-viscous or dry fluid known as the Euler fluid, Euler equation. So this is important to mention that this ideal fluid is dry. It sounds like like nonsense, because how fluid could be dry. But in this sense that it's not how viscosity, it's common thing that it call it dry. But of course it's not dry. But nevertheless, so it constitutes the Euler equation. This equation contains This equation contains derivatives of velocity not higher than the first order, so it's important. So it's actually linear. That is why the flow of an ideal fluid is fundamentally different from the flow of a real fluid, which are determined by the viscous force F with F nu. Containing second spatial derivatives of velocity. Thus, a real fluid is described by equation of a higher order than an ideal fluid, which determines a huge variety of complex phenomena, most of which have not yet been fully studied. So there is a principal difference between the Euler equation, which is actually linear because it not includes the non-linear term, and also with the full system, which includes the viscosity. Viscosity is a very important term because it has producing the highest derivatives of the system. So sometimes even when viscosity is small in any relative units, it's impossible to remove this viscosity. And also I show in this course that namely this viscosity determines even when it is extremely small. Even this viscosity can determine the flow and all the picture of this flow. So, but another disadvantage of the Euler equation is that it's, as I already told, can make some sort of the breaks between different stuff, because there is not smooth translation, because viscosity is even on the small distance could give you the smooth transversity, but sometimes people working in this dry ideal hydrodynamic, there are also some results there, but they basically a bit artificial. So the leading term in the currently accepted approximation for the viscous force F nu was first proposed by the Navia, and there is, we have dates. So this was proposed by the Navia. So we are speaking about this equation in 1827. 1827. So it's about 200 years ago. It's about 200 years ago. Together with equation 7, this equation 7 which you show, so actually Navia invented it in 1827. But in 1845, Stokes considered the motion of tea leaves when stirring a cup of tea with a spoon. So he was fond of tea. So he just stirred the cup with a spoon with the tea and wrote down the equation and viscosity force in the modern form. So he wrote this equation. Okay. This is the modern form of viscosity term. And Stokes wrote it like that. F nu vector. Oh, I forget here to put the vector, sorry. This is quite usual form, and it constitutes two viscosity coefficient. One of them is related to the Laplacian of the velocity, and another is related to the gradient of the divergence. So it's formula 1.9. We also will speak about this lambda term and gradient term. And this term is here. There is it can operate. This operator can operate like we have derivatives in all the three coordinates, and we multiply by these derivatives as a scalar field on the velocity. So we can just operate with this nabla operation in such a way. And here we have a divergence. And here there is a gradient of the divergence. And basically, of course, it's not our case, because the divergence is rather small in the planets. So, of course, there is some, but it's rather small. And usually, most often, it's neglected by them. But, of course, there are some situations where divergence is important. But in any situation, this Laplacian term is important. It's always on top, and it's always determines the property of the fluid. Of course, there are some situations, especially in the sun, by the way, where a divergence is very important. It's because, for example, on the sun, there is same variation of, in 7 orders of the density, so the divergence becomes quite important. Since the end of the 19th century, equation 7 with viscous force 9, equation 7 with viscous force 9, I think that you remember by heart now equation 7. I show you. It's invented this equation actually, all the main ingredients of this equation in 1827, and only after that, in 18 years, Stokes invented actually the same, and he divided this honor of the invention with Navier. But okay, now everybody knows this equation as Navier-Stokes, not just Navier. because Navier not so active and Stokes was very active. And sometimes people in this ancient time getting some result and was not in a hurry to publish it. They just kept it, and many times passed it, and there are many laws which was not granted to the society. Sometimes even these people think that why I will give such a wonderful law to the people. Maybe still there is some who keeping this secret. So in this case, the first dynamic viscosity coefficient, mu, this first dynamic, okay, I can show by mouse, this first viscosity coefficient, nu, and the second dynamic viscosity coefficient, so it's got a special name, the dynamic viscosity coefficient. Zeta are constant everywhere in time. So the simplest form, of course, is Navier-Stokes equation, that generally speaking, this viscosity we can determine almost near each stress term, but it's maybe overworking the size of the problems, because actually it's good, especially in considering this stuff which you consider here. It's important to account both volumetric and other possible changes in viscosity, as told, it's able to determine from the variation of the stress tensor. The definition of one of the components of this tensor is given for the Cartesian coordinate system in Formula 1 above. Formula 1 above. Oh, no. So, however, actually Cartesian coordinate system in Formula 1 above, and the others are discussing solution to the problem 1.4.1 below. Actually, so to this definition, I'm addressing you to the problem which will finalize this this chapter. However, for the vast majority practical application, the simple expression 9 is quite sufficient. Simple, it means that all this viscosity coefficient may be in the worst case only on radius, spherical radius, but not depend. There is no other coefficient which could appear in a more complicated situation, and we think that we will not work with such a complicated situation because even with such an accuracy, this viscous coefficient is very poorly known. So we can manage the constant viscosity coefficient. So the complete hydrodynamic system of equation, of course, there is a main equation which is Navier-Stokes equation, but should be another equation. It's just one. And the complete hydrodynamic system of equation, in addition to the Navier-Stokes equation, bingo, equation 7 and 9 also contains an equation for mass transfer. Here we consider transfer of momentum, and there is equation which considers direct mass transfer or conservation of the matter, which is widely known as the standard continuity equation form. Yeah, you see here, I'll write down it. Okay, I'll write down it like here just to the space. So we have partial derivatives of the density in time plus divergence of density multiplied by velocity vector, and all of this is equal 0. So it's 110. The system for the momentum and mass from the first split equation 7, 9, and 10 for three components of the velocity vector U and scaling pressure P is completely closed by the no-slip condition for the fluid at solid boundaries. And this no-slip condition is again is very simple. Actually, it could be added to this equation. I brought it here. So it's very simple. So, but we should stress that it's exactly on the boundary, and this boundary rotates together with all the board. So it just equals 0. So it's 111. So it's necessary to stress that the value of three components of the velocity vector is considered here on a solid or rigid surface in a coordinate system associated with that surface. Of course, if we consider another coordinate system, for example, when one boundary is rotated, another not rotated, so we should have involved another condition. We are related to the rotation of this. But nevertheless, in coordinate system which is connected, linked to this, so sometimes we have the cases when we should stay in one coordinate system at one boundary and another coordinate system at another boundary. So we should make to apply in one, eventually we should have one system. So should rearrange from one boundary to another boundary to get the proper boundary condition. And boundary condition actually finalizes this problem. actually the boundary condition is the main things which is give us possibility to choose the right solution. And if we restrict ourselves entirely to the hydrodynamic approximation, then from the point of view of thermodynamic, density rho should be defined as a function of pressure P. So this system has two thermodynamic variables, the pressure and density. So since the density variation are small in the course of the planet, here, for example, sorry? No connection. Okay. So, since the density variation are small in the course of the planet considered here, for example, less than 10% in the liquid pore of the Earth, then the roughest or initial approximation, the simplest definition is rho is equal constant. Is completely justified stating the constancy of density everywhere. In this case, the continuity equation is simplified to the widely known incompressible equation. Divergence of U is equal naught, and in 9 the second velocity can be discarded. So actually, did I wrote that? No. Oh. Okay, it was to wrote, it's not wrote here on the presentation. But this formula, while it is not received the number, but nevertheless it's a rather important formula. If we consider the particular case of this situation, when rho is constant, then from that we have, let it put it this way, in that case we have, you see that if rho is constant, then we have the 0 here, and if rho is constant, it's actually could be going from these brackets, and eventually we have divergence of U is equal 0. And it's a very important case, which is basically explored in all approximation. However, this case is somehow also important, but also could be some small variation of the density. And if we have this small variation, we can take them into account in the linear approximation, and it could be the base of the convection, which you consider later. So in this case, it's finally, let's finalize this chapter with a completely known force F and constant density rho. We obtain a system for four-scalar equation for determining the pressure and three components of the velocity vector based on corresponding boundary condition 11. So actually, we may write down the final system. There is still place here. So boundary condition 11 we should mention again. This boundary condition, again I stress that it's in the coordinate system which rotate with the boundary, and if the boundary rotates with different, so it will be some difference. But eventually we write down the important case of the system which we will consider further in the following chapters. And so it's constitute all the equation which we need for to solve the problem. And this is, of course, first of all, Navier-Stokes equation. du by dt plus u. So, and equal. So in this case also dynamical part of the viscosity vanished. So in this case we can write down here only general part of the viscosity. Dynamical viscosity is omitted because the divergence is equal not. And so here we have like that. And then all other forces here, then we minus gradient P, and we divide everything with density. And there is still divergence of the velocity field equals 0. So this is equation 112. Okay. Okay, it seems we finished this chapter. So the next chapter will be rotating coordinate system. Okay, so maybe we can stop. Yeah, please ask a question, if any.
Equation 1.9.
1.9?
Yeah.
This?
Yeah.
Yeah.
So that equation is applicable only to Newtonian fluid, right? Because it doesn't hold for non-Newtonian. And the relationship between stress and strain rate is non-linear.
Yeah, it's Newtonian. It's applicable only to the Newtonian.
So when you deal with interior of, let's say, stars where the fluid is plasma, it doesn't apply.
Yeah. In some approximation, of course, it's possible to apply, but in some case, of course, it's also cannot apply. But in this case, of course, we should consider some addition which could be replacing this stuff. One more question? Okay. It's cool to hear you. I mean,
So you mentioned that this approximation can be applied, so this divergence condition for velocity can be applied for example, then the convection in the south. But as far as I know, in a lot of models that applied for some dynamo, they use Kuznets approximation, and they got some
they are really applied because it's much easier to use the non-divergent condition than divergent condition. So the people are actually making the solar approximation. They're using viscosity, they're using that it's non-divergent, and so it's they are looking at the place where is the light, not there is no light. The situation is, of course, very complicated, especially because there is a huge variation in the density. So actually, in its full, the Business system is not approximated. But if we make to move to the
correlate them with the observations and the experiments?
You mean this approximation?
These equations, we have so many assumptions,
Yeah.
approximations.
Yeah.
How we can correlate them with the experiments and the observations?
We can correlate this with the experiment because the experiments which are have to deal with rotating spheres and some gap between them. In little survey, some of them I showed to you. So we can make some direct experiment which is possible to compare with this theory. And also there is of course some model which can test the Earth's interior and to find, at least to estimate what the conditions there. And in this case, maybe the situation in Earth is better.
In the terms that we can more precisely and with less errors to approximate the system in the Earth, while in Sun the situation is much more complicated. It's quite difficult, namely because this term, this nonlinear term, in Sun is playing crucial role. But in the situation with Earth, this term has a very minor role, so we can work in such a situation when this main non-linearity is also not important. And so it's possible by some methods to model the planetary situation and the Earth, of course, situation to much more accuracy than for the Sun, if compared with Sun. It's a star, of course.
From where that the turbulence is coming? Turbulence is given by which terms?
Turbulence is given directly by this source. Okay, this source is all the source of the problem. It's non-linear, turbulence also coming from here, because usually people name it even a Reynolds stress term. So it's exactly from here turbulence is born. And of course the simplest estimation of the turbulence, if we compare this term and this viscosity term, you see that if you just take this u, and because here there is a derivatives, if you take this u and
some characteristic size, you can directly have the estimation of the turbulence. You just take the velocity average multiplied by the typical distance, and in the order of magnitude you will obtain turbulence viscosity. So it's directly come from this term. Yeah.
But in the Earth we are considering this is negligible. In the Earth, in the modeling of the dynamo models,
Yeah.
for the Earth, if we consider that term has a negligible effect, very small, then how to model the turbulence?
You mean viscosity has a relation with it?
Non-linear term.
Non-linear term. It depends actually. If we consider the situation with Earth, it has almost negligible effect. But in the case of the Sun and stars, it has very many.